The moment you see a model perform brilliantly on training data, you should feel both excitement and caution, because that is exactly when overfitting likes to hide. Overfitting is what happens when a model learns the training set too specifically, including noise, quirks, and coincidences that will not repeat in new data. Beginners often assume that more training and more tweaking automatically means a better model, but a model can improve on training examples while quietly becoming worse at generalizing. In security and cloud environments, this problem is especially costly because the data shifts, user behavior changes, and attackers adapt, so memorized patterns age quickly. Preventing overfitting is not one magic trick, but a discipline that combines incentives, stopping rules, and honest evaluation. Regularization, early stopping, and validation discipline are three complementary controls that keep learning pointed at durable patterns instead of temporary accidents. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A practical way to understand overfitting is to think about what the model is rewarded for during training and how easily it can invent a story that fits the past. If the model has enough flexibility, it can build an internal rule for almost every odd corner case, especially when the feature space is large and the dataset is not huge. That flexibility can look like intelligence because training loss drops, but it can also be a sign that the model is collecting trivia instead of learning principles. Overfitting becomes more likely when labels are noisy, when rare categories are overrepresented through encoding, or when leakage-like shortcuts exist in the features. It also becomes more likely when you repeatedly tune choices while looking at the same validation set, because you begin to fit the validation set indirectly. Preventing overfitting starts with treating generalization as the goal, not training perfection, and it continues with methods that control how wild the model is allowed to become. Regularization is the first major tool, and the simplest way to describe it is that regularization is a cost you add for complexity. Instead of telling the model to only minimize error, you tell it to minimize error while also paying a penalty when it uses extreme parameter values or overly detailed patterns. This changes the model's incentives in a way that usually makes it prefer smoother, more stable explanations that generalize better. In many machine learning, ML, settings, regularization has the practical effect of shrinking weights so no single feature can dominate unless it has strong, consistent evidence. That matters in cloud and security data because many features can be correlated proxies for the same behavior, and large weights can amplify noise. Beginners sometimes think regularization means making the model weaker, but a better framing is that it makes the model more cautious about claiming certainty without support. It also helps to connect regularization to the bias-variance balance you learned earlier, because regularization is one of the main knobs for controlling that trait. When you increase regularization, you usually reduce variance by discouraging the model from fitting tiny quirks, but you may increase bias if you push too hard and block real structure. When you reduce regularization, you usually lower bias because the model can fit more nuanced relationships, but you increase variance risk because it can memorize noise. The goal is not to maximize regularization or minimize it, but to choose a level that matches how much evidence you have. In practice, the right amount depends on dataset size, label quality, feature redundancy, and how stable the environment is over time. In a fast-changing cloud environment, slightly stronger regularization often helps because it encourages patterns that are broad and durable instead of patterns tied to one short-lived configuration. Regularization is not only about numeric penalties on weights, because many modeling choices function as regularization even when they are not called that. Limiting model depth, limiting the number of splits, restricting the number of parameters, or forcing simpler functional forms are all ways of controlling how detailed the model can be. Even feature selection can act as regularization by removing weak or noisy inputs that invite memorization. For beginners, this is an important mindset shift. Regularization is a family of complexity controls, not one specific formula. The unifying idea is that you are preventing the model from building a fragile rulebook that only works on the training set. In security analytics, this can mean resisting a model that keys too strongly on a specific error code or a specific tenant behavior that might vanish after an update. A regularized model may feel slightly less sharp on training data, but it often behaves more predictably when conditions change. Early stopping is the second major tool, and it is best understood as a time-based form of regularization that prevents the model from training past the point where it starts memorizing. Many training processes improve general patterns first, and then, with enough iterations, begin fitting noise more and more closely. Early stopping uses validation performance as a signal for when that tipping point has arrived, and it stops training before the model crosses into memorization. This approach is especially common in iterative training methods where the model is updated in many small steps, because overfitting can build gradually. The key beginner insight is that more training is not always better, because training can move from learning signal to learning noise. Early stopping makes training behave more like learning a useful summary rather than writing down the entire training set. In cloud security contexts, where data can be noisy and drift, early stopping often reduces the risk of learning patterns that will not survive the next system change. To use early stopping well, you need a clear view of what you are monitoring and what the curves are telling you. If training loss keeps going down while validation loss stops improving and begins increasing, that gap is a classic sign that overfitting is starting. Early stopping chooses the point near the best validation performance and treats that as the best generalizing model, even if training loss could be lower later. Beginners sometimes misinterpret this as giving up too soon, but the validation curve is a proxy for future performance, so ignoring it defeats the purpose of evaluation. Early stopping also depends on patience rules, meaning you often allow a few steps without improvement before stopping, because validation signals can be noisy. The broader discipline is that you stop training based on generalization evidence, not based on how satisfying the training curve looks. If you learn to read these signals calmly, you avoid the trap of training until you feel accomplished instead of until the model is actually ready. Validation discipline is the third tool, and it is the foundation that makes both regularization and early stopping trustworthy. Validation discipline means you treat validation data as a stand-in for the future, which means it must be kept separate, it must reflect realistic conditions, and it must not be used as a playground that you repeatedly optimize against without restraint. A common beginner error is to tune dozens of choices while watching validation performance and then report the best score, as if it were an unbiased estimate of future performance. The problem is that repeated tuning on the same validation set effectively trains you, the human, to fit that validation set, which is another kind of overfitting. Strong discipline includes holding out a final test set that you touch only at the end, and using cross-validation, CV, carefully when appropriate to reduce luck from one split. In time-aware settings, it also means avoiding random shuffles that leak future patterns backward in time. Another part of validation discipline is matching the split strategy to the kind of data you actually have, because overfitting can be hidden by unrealistic splitting. If your data includes repeated events from the same user, device, or account, splitting individual rows randomly can leak identity patterns across training and validation, making performance look better than it should. If your data spans time, splitting randomly can expose the model to future distributions during training, which reduces the apparent difficulty and inflates results. In cloud security analytics, these issues are common because activity logs are naturally grouped by identity and ordered by time. Discipline means you split in a way that simulates deployment, where the model must handle new time periods and possibly new entities. When you do this, overfitting becomes easier to detect because the validation set is truly different in the ways that matter. If you do not do this, regularization and early stopping can still help, but you may be optimizing against a misleading mirror. Regularization and early stopping also interact in a useful way that beginners should understand, because you do not have to pick only one. Regularization controls how complex the model can become at any point, while early stopping controls how far the training process is allowed to refine that complexity over time. When used together, they often provide a stronger defense than either alone, especially when you are working with many features, sparse encodings, or noisy labels. A model that is lightly regularized but trained for too long can still overfit, And a model that is strongly regularized but trained with poor validation discipline can still be tuned into fragile behavior. The combined mindset is that you want a model that is capable enough to learn real structure, but constrained enough to avoid chasing every random bump. In security contexts, this balance matters because false positives create operational fatigue and false negatives create risk, so stability and calibration often matter as much as raw accuracy. It is also important to notice how feature engineering choices can either reduce overfitting risk or accidentally increase it, because prevention is not only about training controls. When you create many one-hot categories, you create a sparse, high-dimensional space where rare categories can be memorized. When you create target-like encodings carelessly, you can create leakage, which is the most extreme form of overfitting because it teaches the model to cheat. When you create meaningful ratios and stable aggregate features, you can reduce overfitting because you are giving the model signals that generalize across entities and time. This is why validation discipline is tied to feature discipline. Every engineered feature should be defensible as something known at prediction time and stable enough to repeat. If you treat feature engineering as a way to chase training performance, you will create brittle features that invite overfitting. If you treat it as a way to encode real-world structure, you reduce the temptation for the model to memorize. Another beginner misconception is that overfitting is always solved by making the model smaller, but sometimes the real issue is that the model is being asked to learn from inconsistent labels or inconsistent data collection. If the target is noisy, the model can overfit by learning label noise patterns that will not repeat. If logging changes create shifts in feature meaning, the model can overfit by learning patterns tied to a specific logging version rather than to the underlying behavior. In cloud settings, telemetry pipelines evolve, and a field that used to mean one thing can change subtly, which can create apparent overfitting even when the model is not overly complex. Prevention here involves data governance and monitoring, not only training tricks, because a stable learning problem requires stable definitions. Regularization can soften the impact, but it cannot fix a moving target. Validation discipline helps you detect these issues early by revealing performance drops when the data-generating process changes across time windows. You should also learn to recognize overfitting in the way errors behave, not just in summary scores, because trust comes from understanding failure modes. Overfit models often make very confident predictions in situations where they should be uncertain because they learned sharp boundaries from limited evidence. They may also behave inconsistently across groups, doing very well on segments that resemble the training distribution and poorly on segments that are underrepresented. In security workflows, that can show up as a model that flags one department aggressively because it learned a quirk of that department's historical data, while missing threats in another department whose patterns were rare in training. Regularization tends to reduce these extreme swings by forcing smoother decisions, and early stopping tends to reduce them by preventing the model from refining quirks into firm rules. Validation discipline ensures you can see these patterns before deployment by evaluating across time and across meaningful segments. When you combine these perspectives, you start trusting the model for the right reasons. A final piece of prevention is to treat model selection as a controlled experiment rather than an endless search, because endless search invites overfitting to your evaluation process. If you try hundreds of model variants and choose the best one based on a single validation set, you are likely selecting a lucky winner rather than a genuinely better approach. This is why CV and test holds exist, and it is why documenting what you tried matters, even for beginners. You want improvements that are robust across splits and time windows, not improvements that appear only once. In cloud and security applications, where the cost of failure can be high, this discipline is part of responsible engineering, not academic perfectionism. Regularization and early stopping help inside one training run, but validation discipline helps across many runs by keeping you honest about what is real. When you adopt that mindset early, you build habits that scale as problems become more complex. By the end of this topic, you should see overfitting prevention as a coordinated set of controls that keep a model focused on patterns that will survive contact with the real world. Regularization changes incentives by penalizing excessive complexity, encouraging stable solutions that do not rely on fragile quirks. Early stopping uses validation evidence to halt training before the model shifts from learning signal to memorizing noise, especially in iterative learning processes. Validation discipline makes the entire process credible by ensuring splits reflect deployment reality, by limiting repeated tuning on the same validation set, and by using tools like CV and held-out testing responsibly. Together, these practices protect you from models that look impressive in development but behave unpredictably in production, which is a common failure mode in real data systems. When you build these habits now, you are not just improving accuracy, you are building trustworthiness. And that is the property that makes data AI work valuable over time.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.